Stay safe, happy learning. Resistance, inductance, and capacitance are passive circuit elements. In resistive circuit of in AC resistive circuit, the current is in phase with voltage. In inductive circuits, the current lags by 90 degree, and in capacitive circuits, the current leads the voltage by 90 degree. Active power is watt or kilowatt. Reactive power is watt or kilowatt. And apparent power is kVA. Power factor is defined as the index of proximity of a given load to resistive load. Thus, the second definition of power factor is equal to Kw vectorial form, Kw divided by kVA. This is equal to here. This is an inductive circuit. Pure this is an inductive circuit wherein the current lags the voltage by 90 degree, and vector sum of this active power and reactive power is apparent power, kVA. So power factor is equal to Kw by kVA, and kVA is the vector sum of Kw and kVAR. So power factor is equal to vector Kw divided by vector Kw plus kVAR. In ideal condition, the angle between Kw and kVA will be 0. So this will coincide with Kw. So another definition of power factor is the cosine of angle between real power that is Kw and reactive power, apparent power that is kVA. Here angle between real power and apparent power is phi. So power factor will be cos phi. PF is equal to cos phi. Cosine of angle between OA and OB, that is real power and apparent power. However, this relation holds good only with sinusoidal waveform. For sawtooth waveform or square waveform or any other non-sinusoidal waveform, this relation will not hold good. Internet is filled with the material suggesting power factor to compare with a beer glass, wherein the liquid portion is kilowatt, the end of liquid to end of foam portion is kVAR, and the total is kVA. This describes power factor even if thought correct in algebraic sum of kW and kVAR. That is wrong. kVA is vector sum of kW and kVAR. So this is rejected. Now poor power factor are the worst enemy of a power system. The poor power factor may cause complete failure of the system and economically largely damaging to the system. The power factor at which AC machine operates is an economically important feature because of the cost of reactive kVAR. Low power factor adversely affects system operation in mainly three principal ways. In the first place, generators, transformers, conductors, etc. are rated in terms of kVA rather than kilowatts because their losses and heating are very nearly determined by voltage and current regardless of power factor. The physical size and cost of AC apparatus is roughly almost proportional to its kVA rating. The investment in generators, transformers, and transmission equipment for supplying a given useful amount of active power therefore is roughly inversely proportional to the power factor. Secondly, low power factor means more current and greater copper loss in generating and transmitting equipment. Third disadvantage is poor voltage regulation. Factors include influencing reactive kVA requirements in motors are visualized readily in terms of relationship of these requirements in establishment of magnetic flux. As in any electromagnetic device, the resultant flux necessary for motor operation must be established by a magnetizing component of current. It makes no difference either in the magnetic circuit or in the fundamental energy conversion process, whether this magnetizing current be carried by rotor of synchronous machine or stator of induction machine. It makes no difference in magnetic circuit. Just as it makes no basic difference in a transformer which winding carries the exciting current. In some cases, part of it is supplied from each winding, that is primary and secondary or stator and rotor both. If all or part of the magnetizing current is supplied to an AC, the input to that winding must include lagging reactive kVA because magnetizing current lags voltage drop by 90 degree as I discussed earlier. In effect, lagging reactive kVA sets of flux in the motor. The only possible source of excitation in an induction motor is the stator input. When input is given to a stator, There creates a rotating magnetic field in the air gap between stator and rotor. The induction motor therefore must operate at a lagging power factor. This power factor is very low at no load and increases to about 85 to 90% at full load. So even at full load, the power factor corrections are required. Power factor can be corrected with the help of either condensers or capacitors or synchronous motors or synchronous machine known as synchronous condensers. With synchronous motors, there are two possible sources of excitations: alternating current in the armature or direct current in the field winding. If the field current is just sufficient to supply the necessary MMF, no magnetizing current component or reactive kVA is needed in the armature, and the motor operates at unity power factor. If the field current is less, that is, the motor is underexcited, the deficit in MMF must be made up by the armature and motor operates at lagging power factor. If the field current is greater, that is, the motor is overexcited, the excess MMF must be counterbalanced in the armature, and a leading component of current is present. The motor then operates at a leading power factor. Because magnetizing current must be supplied in inductive loads such as transformers and induction motors, the ability of overexcited synchronous motor to supply lagging current is a highly desirable feature which may have considered economic importance. In effect, overexcited synchronous motor act as generators of lagging reactive kVA and thereby relieve the power source of the necessity for supplying this component. They thus may perform the same function as a local capacitor installation. Sometimes unloaded synchronous machines are installed in power systems solely for power factor correction. However, such installations are done over 600 kVA capacity only, and such machines are called synchronous condensers. Maybe more economical in the larger side. Yes, definitely more economical in the larger side. Both synchronous and induction machines may become self-excited when a sufficiently heavy capacitive load is present in their stator circuit. The capacitive current then furnishes the excitation and may cause serious overvoltage or excessive transient torque. Because of the inherent capacitance of transmission lines, the problem may arise when synchronous generators are generating long, unloaded, or lightly loaded lines. The use of shunt reactors at the sending in of the line to compensate the capacitive current is sometimes necessary. For induction motors, it is normal practice to avoid self-excitation by limiting the size of any parallel capacitor when the motor and capacitors are switched as a unit. So we see for induction motors, we do not require excitation through any capacitor. The single phase capacitor start motors are used only to create phase difference between rotor and stator, not for excitation of the motor. Thank you. That's all in this video. Stay safe, happy learning, conserve energy.